So basically all through this week we've been talking about how to view Einstein's equations or how to reformulate them as a set of evolution equations that allow us to take some data on some initial time slice and evolve it forwards in time. And we've talked about how on each time slice the metric quantities just on that time slice have to satisfy some constraint equations, the so-called Hamiltonian and momentum constraints. And we also talked about that as long as we start off with some initial data that satisfies those constraints, our evolution equations will ensure that at later times these constraints will still be satisfied. But what we haven't talked about yet is how do we actually solve these constraints, at least at the initial time. And also about this sort of the larger problem of just how do we choose these metric functions on our initial time slice to actually represent the physical system we're interested in. So that's going to be the subject of today's lecture. And also if you're interested in another reference for this, you can check out these lecture notes. So chapter 8 will cover this initial data problem, and also some of the earlier chapters also cover this 3+1 decomposition and so on that we talked about earlier in the week. Yeah, so when addressing this initial data problem in GR, we basically have two goals that are somewhat at odds with each other. So the first one is just when we want to choose our 3 metric and our extrinsic curvature at initial time such that the Hamiltonian and momentum constraints are satisfied. So let's just write those down. Where this is the Ricci scalar on our 3 manifold. And I'm going to use E here to denote the energy density, but that's just the projection of our stress energy tensor. With respect to these, our vector that's normal to our slices of constant time, and then the momentum constraint. And this is the momentum density here. So that's goal number 1 is we have to satisfy the constraint equations. Otherwise, we can't say we actually have a solution to the Einstein equations. But our second goal is that we actually want to, choose these functions, these metric functions, such that they actually represent the physical system we're interested in. At least as closely as possible. So the sort of usual approach to this problem is to basically divide up these quantities into 2 different groups. Basically, one we'll call the free data, which will specify freely to represent our physical system, and the rest will be the constrained data, which will basically choose by solving some version of these 2 sets of equations. So we're going to divide our degrees of freedom into free and constrained data. So sort of the challenge of this initial data problem is basically to make it so that this free data is something we have some sort of physical intuition about, but also something where the remaining sets of data actually, the equations that they have to satisfy in order for these Hamiltonian momentum constraints to be satisfied actually are sort of well-posed equations that we can solve. In the general cases we're going to look at here, they'll be elliptic equations, and so we want them to choose them such that they have nice properties, like they have unique solutions, and there exist solutions to them. And for example, like one thing we wouldn't want to do is just, for example, say, choose one component of the metric and then solve for the other component of the metric or something like that. That would give us very ugly equations or things like that. So if we just count these degrees of freedom, we can see that we have 4 constraint equations, the Hamiltonian and the 3 components of the momentum constraint. And the total number of degrees of freedom we have, and the 3 metric and the extrinsic curvature, it's just 6 in each because they're symmetric 3x3 matrices, so we have 12 total. And that means that we need to specify 8 degrees of freedom, right? And plus the matter. So one common approach that we're going to follow here is to basically use a conformal decomposition of the matrix of the for a metric, and also do a trace decomposition as well. So in order to do that, it's going to be helpful to have some to write down some formulas that basically describe the behavior of a metric under a conformal transformation. So I'm not going to derive these. You can find them, for example, in like one of the appendices in Carroll, or also in this reference here. So let's say we have a conformal transformation. Here, this will just actually, I'll first do the general case. This is just an n-dimensional matrix, or sorry, an n-dimensional metric. And it's conformally related to this metric G tilde. And we basically want to know how all our various geometric quantities transform. So the main thing they'll be interested in is basically the difference of the Christoffel symbols calculated with this guy compared to those calculated with this metric. So the difference in 2 Christoffel symbols should give us a tensor. We can write it like this, and if you crunch through all the math, what you get is the following. And so then we can use this relation between the Christophel's and one and the other metric to derive some other things. Scalar derivatives, of course, don't change because they're just the same as ordinary partial derivatives. But the vector ones do change. Okay. That's how the covariant derivative of a vector transforms, and then another one we'll need to use is how the Ricci curvature changes. Okay, so take a long time even just to write down. But also one thing to note is that how the Ricci scalar transforms on these conformal transformations actually depends on the dimension that we're looking at. And so, in fact, you can see that if you have like a metric that's four-dimensional, then with n equals 4, you don't get these cross terms that are two partial derivatives of this conformal transformation. So it actually will turn out that when we're working with the 3 metric, we want to choose the following. We'll want to choose, instead of this power of 2, a power of 4. So okay, so these are just the general formula that we'll use today, but the approach we're going to take for basically decomposing our 3 metric extrinsic curvature is to start with this conformal decomposition, where we'll let the 3 metric be given by our conformal factor psi to the 4th power, and then a conformal metric. And basically, this we will choose freely. this we will solve the Hamiltonian constraint for. And if we basically plug this transformation into this formula and specialize to the case n equals 3, you can convince yourself that the sort of cross terms we get that are single partial derivatives from basically letting omega squared equals psi 4 will cancel out. And so we get the following. Yeah, and just to emphasize, yeah, these should all have. Yeah, so to emphasize here that the tilde over this just means the covariant derivative with respect to the tilde metric, and so on, and here as well. Yeah, and so that's how we decompose the 3 metrics. So now we're going to start decomposing the extrinsic curvature as well. And we'll start by decomposing it into a traceless part and its trace. So then this by definition is trace-free. And then this quantity, we'll actually find that we want to conformally rescale it to make our life easier by the following power. So we'll see in just a second why we chose 10 here. Yeah, so using these new variables, we'll plug those into the Hamiltonian constraint we have up at the top there, and we get the following. Okay. And again, to emphasize, all these quantities that have the tilde over them are now, we can calculate just with respect to this conformal metric, gamma ij tilde, which we're going to specify. So this is beginning to look more like an elliptic equation. We have something like a Laplacian operator with respect to this conformal metric. And then we have some source terms here, but basically the main derivatives. So this is something that we can hope to maybe solve to get the conformal factor. So any questions about that so far? Okay, so let's turn to the momentum constraint. So the first term in the momentum constraint is this one. And plugging in this trace decomposition. We get this, and we just work out what this guy is in terms of our conformal metric. With these C's, which we just said with the difference in the Straffel symbols from our regular metric and the conformal metric. And if you work through that, you get something like the following. And this last term that we get for a general tensor, we can notice that this is actually just the trace of A. And so by construction, this is trace-free, so we can get rid of this last term. So we just have these two terms here. And now we can see where this magic number 10 comes from. So we have the covariant derivative of the log of psi here. So we can actually take this and convert it to a power for psi. And just write this whole thing as the following. And then using this, hatted Aij, we just get this. Okay, so what does our momentum constraint look like now? Okay, so things are looking better, but we still basically have some sort of tensor here. We have this derivative operator acting on it. So we still don't quite have it in this nice form of a Laplacian of some variable with some other terms. So we still need to further decompose this A hat. And the way we're going to do this is we're going to basically decompose it into a longitudinal part and a transverse part. And so again, this is going to become our free data that we're going to choose freely. And this vector x is what we're going to end up solving for. So let me tell you what these different things mean. So first of all, this TT transverse traceless. So that's just the usual definition that when you contract it, this tensor with a covariant derivative in the j direction, then we get 0. And we already subtracted out the trace parse. So this is traceless as well. And then x here is going to be our vector potential. And then this L tilde here is a conformal killing operator. So okay, so that's the form that it takes right there. And we can note that it's symmetric. If we switch the indices, we just get the same thing. And it's also traceless because this guy is traceless and these are traceless, so this has to be traceless as well.
And what makes it longitudinal? That it's not transverse?
Yeah, that basically we have a general tensor and we subtracted out the transverse part, so it's the part that remains.
Okay.
Okay, so now we're in the position to define the conformal Laplacian of this vector potential x. So we'll denote that with this delta L. And it's just going to be equal to this by the transverse property. So, in general, you might worry that not all tensors can be, tensor fields can be decomposed this way. That, so that we can find a vector potential that actually will give this longitudinal part. But you can actually show, at least in the case where you're asymptotically flat or in a closed manifold, which would be the main ones of interest, that your tensor will emit a decomposition of this form. So you can check out that reference which I just erased. In the appendix, they give the proof of that. So if we plug this in, we're beginning to have some elliptic-looking equations. So let me just rewrite the Hamiltonian constraint using this. So in our conformal transverse traces, the Hamiltonian is this. I'm just going to put a square here to mean contracted with the same thing with the indices raised. And then our conformal transverse traceless version of the momentum constraint. So we still haven't decided basically how we want to conformally transform our matter components. So I've put a tilde here, but left this this exponent m and similar tilde for the energy and this exponent n here. So what you need to decide is basically how we want to conformally rescale these as well.
How is that you get a choice? Is you just call it a name? You have a choice because you have like freedom in doing, seeing how you rescale them? Because it's just a name, you're saying this is going to be...
Yeah, so,
okay.
So like ideally you might want to think that I just choose what my energy density is and the momentum is on the initial slice. But it turns out that it's actually hard to do that, and sometimes that'll make the equations more difficult to solve, or maybe even make it so there's not a there doesn't exist or there isn't a unique solution. So in general, we might just take these to be 0, but we'll show in just a second that it's actually better to take them to be something else, and then we choose the sort of conformally rescaled energy density moment, and those are our free data. And then once we solve all the equations, we'll get out something that's a bit different.
But the physical intuition you have on these scaled energies and momentums is like not as good as the one you have for the ones that are not rescaled, right?
Yeah, in some sense, we're not choosing exactly what the energy density is on the metric, but I'll show you in a second how maybe we don't necessarily want to do that.
Okay.
Yeah.
That exponent you have on the side there, the negative n plus 5, right there at the end, is that like, yeah, is that negative, is it like in a bracket, the n plus 5? Like if n was 5, then does that just go to 0 and then 1?
Yeah. What do you mean, like that?
Or the bracket inside of the negative. So it's negative of whatever n plus 5 is.
It's 5 minus n.
Okay.
Yeah. Okay, any other questions? So if we look at our momentum constraint, we can immediately notice what might be a good choice for m, right? So we're gonna choose the trace of our extrinsic curvature, and that's gonna be free data. Perfectly valid choice would be to choose it to be constant, in which case this middle term would disappear. And then if we further make the choice that m equals 10, then this dependence on the conformal rescaling psi would disappear completely from our momentum constraint, which means these two equations would no longer be coupled, right? Right now they are coupled, or this one would still involve quantities determined here, but we could solve the momentum constraint first independently and then just plug the answer we get into here. If we didn't do that, then we have to solve them both simultaneously. So that sort of motivates the choice m equals 10. And one, in fact, can show that you get sort of existence and uniqueness of solutions of solutions to this for this vector potential x. Again, in the case that you have an asymptotically flat or closed manifold. Yeah, and so there's a special name people use to describe the k equals constant. That's a constant mean curvature slice. We call it that k is just the mean curvature of this sigma 0 time slice as it's embedded into our four-dimensional manifold. And the special case where k just equals 0 is called maximal slicing, which is also a sort of popular gauge choice. Yeah, so we chose m. Now we want to choose n. So we're actually going to choose the conformal rescaling of energy based on uniqueness considerations. So what we want to do is say we have some solution psi bar to our Hamiltonian constraint, and then we want to look for a new solution psi that's nearby psi bar. So write it as psi bar plus some small quantity epsilon. So these are both solutions to the Hamiltonian constraint. And then sigma is small compared to psi bar. So if we just do an expansion of our CTT Hamiltonian constraint, to leading order in epsilon, we get the following. So, the psi and the psi bars disappear because they're just solutions to the equation already. So we just get this in terms of epsilon. And we're going to call this whole coefficient C. So we just have Laplacian of epsilon equals this C times epsilon. And then what we can do is basically argue that if C is greater than or equal to 0, then we actually have at least local, because we're just only looking for nearby solutions, local uniqueness. And it actually follows by the maximum principle. Which I won't go into the details of, but the basic argument is that if we require epsilon to vanish on the boundary, because we're specifying some boundary conditions for psi, and so psi and psi bars both satisfy them, then basically if this is greater than or equal to 0, epsilon has to take its maximum on the boundary. And same argument for minus epsilon, and from that we can derive that epsilon has to be 0 throughout the whole domain. And we get uniqueness. And so if we don't, so some of these are sure going to be positive definite. But basically, if we don't want our energy to spoil this constant being positive, we better take n to be at least 5. So it turns out a popular choice is actually to choose n equals 8, and I'll show you why that is. So this is actually based on sort of preserving the dominant energy condition. So the dominant energy condition just says that if we take our stress energy tensor and contract it with some time-like vector, then this new vector we get is future pointing causal. And this will be satisfied, for example, by a fluid, or most matter would be interested in. And so if we work out what this looks like in the 3+1 language, it just means that we get the following relationship between the energy density and the momentum. And if we had a fluid or something like that, it would basically say our fluid is not moving at the speed of light or faster. Okay, so why does that imply that we want n equals 8? So that means that say we start off with some conformal energy density and 3 momentum that satisfies this dominant energy condition. Of course, this is the things we're actually choosing. And then we solve our constraints, we get our conformal factor, and then we rescale things. Then the rescaled energy density is just going to have the following scaling. And then from this, we get and then if we work out how all these quantities scale, then we just get the square of our momentum density after it's rescaled. So basically, if we start off with some matter that's not, moving faster than the speed of light, then once we rescale things, our matter still won't be moving faster than the speed of light, for example. Okay, so let's just recap what we've done here. So what is the free data for this conformal transverse traceless decomposition?
The energy. The conformal scale energy. Well, the beat, also the moment, the beat, the conformal beat.
Yeah.
What else? The conformal metric.
Yep.
The K.
Yep. Yeah, and one more thing.
Is that all? The X?
No, so X is constrained data, right?
X is then the other one, the hat dt of A.
Yeah, so A hat, the transverse traceless part of it. And what's the other constrained data?
What's the phi?
Yeah, psi.
Psi is. I always mix my letters.
Okay, so if we count the degrees of freedom and just ignore the matter for now, so we get, for an ordinary symmetric 3x3 tensor, we get 6, but now sort of taken off 1, so we have 5. So we get 5 here, and then we get 1 here, and then we get 2 here.
So what was the argument for the 5 again?
Well, yeah, I mean, basically if I have some solution and then I rescale everything by psi or something like that in the appropriate way, then I'll get a new solution where my solution to psi will also be rescaled by that power.
Okay.
So we can quibble about where to subtract off that degree of freedom, but I'm doing it from this metric. Yeah. Yep, and then here we're solving for basically 4 degrees of freedom. Yep, and then once we solve for these, we can basically reconstruct everything we need. Okay. So maybe just a few remarks. We went through one example of how to decompose the constraint equations called the conformal traceless or conformal transverse traceless decomposition. There are a number of other ones that take slightly different forms. So we won't go through deriving those equations. They're pretty much similar in spirit. But for example, there's the conformal thin sandwich one. And here, basically, again, you choose the conformal metric, the trace of the extrinsic curvature. Instead, you choose the conformal lapse, and then the time derivative of the conformal metric. And then, instead of solving for this vector potential x, you actually solve for the shift vector. So you solve for the conformal factor and the shift. And then there's a variation on that called the extended conformal thin sandwich. Where basically you don't specify the lapse, you specify the time derivative of the extrinsic curvature, and then basically you get one extra equation that relates this to the lapse. And so then you solve for, now instead of 4 variables, 5 variables. And so, yeah, so the reason you might want to do this we'll mention in a second. So yeah, just in the last couple of minutes, maybe like a couple of remarks on how you actually choose this free data. So there are various strategies. So one is based on the idea of using superposition. So let's say, for example, I want to create initial data that describes 2 black holes. Maybe they're have some initial velocities, or they're in an orbit or something like that. So I'll use boosted black holes. Or sorry, I want to describe a system consisting of 2 neutron stars. So in the tutorial, you worked out how to solve individual neutron star solutions, so we can combine those to get initial data to see what happens when they collide or something like that. So one strategy would just be, let's construct all our free data by basically just pretending GR were a linear theory and saying we can basically take the metric of one of our objects, black holes, stars, add it to the metric of another, and then just subtract out the flat space part. And then we can do the same thing with all the other free data quantities.
Subtracting the flat part is for regularization. Why do you do that? Subtracting the flat part.
Well, let's say both my objects have 0 mass or something, right? Mm-hmm. And I just have 2 flat space metrics, right?
Yeah.
And so then I want to subtract out one of them, right?
Okay, yeah. All right. Okay.
Yeah, so like far away, these will both be, you will have 2 copies of Minkowski. Yeah, and so of course, GR isn't a linear theory, so we'll get some correction, but basically we can solve our constraint equations, we'll get some conformal rescaling and so on, and that'll basically tell us how to fix these metrics to actually be solutions to Einstein's equations. Another common trick to use is to basically, if you're looking at quasi-circular in spirals, we have 2 objects in an approximately circular orbit, is to assume that we have an approximate killing vector. It's just the helical killing vector. So we just assume that at some instance of time, we have this approximate killing vector that says that, as we go forward a little bit in time, we just have to rotate our system by the, orbital frequency. And then the system will look the same. So just the definition of the killing vector is that the metric should be approximately 0 when we act with the lead derivative with respect to that. So of course this is not exactly true. If we have 2 objects in a circular orbit, they'll be emitting gravitational waves and the orbit will be shrinking, so it won't be exactly the same. But as long as we aren't sort of in the last stages of merger, this is a good approximation. So that means we can go to a co-rotating frame and basically set all our time derivatives to 0. And so, for example, that's one of the reasons this extended conformal thin sandwich technique is popular, because basically we get as many time derivatives as possible that we can set to 0. Yeah, and so some of the problems, in addition to this, you might have some constraints that you want your matter equations to satisfy. Yeah, so in the tutorial, you guys, when you were solving for these equilibrium star solutions, you were not only solving essentially the Hamiltonian constraint of the Einstein equations, but you're also using the fact that your star was in equilibrium, so it shouldn't have any velocity. The fluid shouldn't be accelerated. There should be this equilibrium between the pressure and gravity. And so you can generalize that, for example, if you have stars in orbit or something, such that in this co-rotating frame, again, the star should be essentially in equilibrium. And yeah, so these are some tricks to sort of help you choose the free data and solve the constraints and evolve forward. But sort of none of these ways of constructing initial data is perfect. So it's very common, if you look at, for example, one of these simulations of a binary black hole merger or something, at the beginning, you'll get this initial burst of high frequency gravitational waves that people refer to as junk radiation. And that's basically just in there because your initial conditions aren't exactly what they would be if you started with the system infinitely far away and evolved it to that point. But usually, this junk radiation just sort of disappears on, something like a light crossing time of the system, and then if you sort of ignore that first part, then your system is sort of a very good approximation to one of these, orbiting binary black holes, for example. So let me end here and take any questions you have.
things like junk radiation. For example, enters like your black hole is like eaten by one of your black holes in the orbit, and then it changes, for example, the mass of this black hole that you first intended to be, or then it doesn't matter because you can like measure it once everything is like clean.
Yeah, I mean there will be some small. Usually, it's not that significant the change in the the sort of gravitational waves that are absorbed by the black hole, but yeah,
Okay.
it will be non-zero. Yeah, so I mean, commonly you can sort of iterate on these things, right? Like you can evolve, see what the mass of the black hole you get out is, and then adjust the input mass to sort of iterate on it to get what you actually want. Okay.